The problem I want to explain today is a gradient estimate. So we assume that there are two inclusions or one domain and an inclusion inside omega, and then conductivity is assumed to be constant outside these two inclusions, or in omega outside this one inclusion, and then conductivity is assumed to be constant inside these inclusions. And I just restrict this PDEs are viscous or balls. And then here the question is, we want to get optimal bounds for the gradient u in terms of the distance between these two inclusions B1 and B2, or inclusion and the domain omega. And this problem is related with the estimation of stress in composite material. Say if we have stiff fiber reinforced, then the cross section is all two domain, and then we are interested in this situation when two fibers are very close related, then the stress could be very large. And in that case, since we have high stress, the material could be very fragile. So we want to drive optimal bounds for gradient u in terms of the distance, and check when the gradient will blow up or not. Okay, here is a related result. In the case the conductivities are away from 0 or infinity, then the gradient u is bounded. There is result by K and Vogelius, and then Professor Lee and Vogelius, that the gradient u is bounded independently of epsilon. And also this work is extended to elliptic system. And there is also unboundedness result for the extreme case, and they show that the gradient generally becomes unbounded if k is infinity, and the blow rate is like 1 over square root epsilon. And I will explain it first for the estimate in the case of circular inclusions, and then drive decomposition of u into blow-up terms and non-blow-up terms. So if we have this decomposition result, then to compute numerically gradient u, that we only need very careful for this blow-up term, and non-blow-up term about that non-blow-up term, the grid could be not that fine. I mean, the problem if we can understand where the problem happened. And then finally I will explain the results on the spherical inclusions, which is result in R3. In 2D case, again the equation is conductivity equation, and then H is entire harmonic solution, and then conductivity is 1 outside B1 and B2, and then K1 and K2 inside B. And then we want to drive estimate for gradient u. So here the idea is that u can be represented as the harmonic function H plus single layer potentials. Since u satisfy the transmit condition, here we have the equation for the potentials on boundary B1 and B2. Here lambda is conductivity K plus 1 over 2 times K minus 1. And if we get this phi 1 and phi 2, then actually gradient u on the boundary is constant times of phi 1 and phi 2. So it is enough to estimate the supernormal phi phi 1 and phi 2. So how can we get phi 1 and phi 2? The main idea is at first we just neglect this term, the singular quotation of phi 2 and then phi 1. Then the phi 1 should be 1 over lambda times gradient h over the nu, and then phi 2 will be just 1 over lambda times the right hand side. And to make phi 1 and phi 2 satisfy the equation, we just modify by adding one more term, which comes from the phi 2 term. And here, modify phi 2 by adding this blue, by putting this blue term inside phi 1, we should get one more term like this. So phi 1 and phi 2 is infinite series. So the phi 1 is infinite series, which is summation of 1 over 4 times lambda 1 lambda 2 k, and then derivative of iterated refraction of h. H is the given background harmonic function, and L1 and L2 is a reflection with respect to the two disks B1 and B2. And to get gradient u on the boundary, we only need to estimate this phi 1 and phi 2. And since it is infinite series related with gradient of iterated reflection of h, and if you look at this gradient term, then it's gradient at some reflected point times Jacobian of reflection. So the question is, how can we get upper bound for gradient of L2, L1 to k times of h? And since we assume that these two inclusions are epsilon distance, then this Jacobian of reflection is bounded by the radius square over some point minus center. So the distance to the center point, absolute value to the square. So it is like 1 plus epsilon times some constant. So since we assume that all the points are away at least epsilon distance, based on this estimate, we get that phi 1 is bounded by 1 over epsilon. So if the balls have epsilon distance, we have at least 1 over epsilon bound. But this 1 over epsilon is not optimal. Again, to get gradient u supernum, the main problem is how can we calculate gradient of iterated reflection of h. So the question is how the reflected point, where the reflected points are located. If the points are away from epsilon, then the 1 over epsilon. But if you look at this figure, then after some step, the reflected point actually located in the square root epsilon distance from this middle point between B1 and B2. So since after some reflections, the boundary points of the balls are 1 over square root epsilon away from the middle point of two balls. So following the calculation, the previous slide, gradient u is bounded by 1 over square root epsilon. And here is the statement of the main theorem. This work is done with Habib Amari, Habib Hyungbae, and then Lee, Jung Lee, and myself. So here we say xj is the point on the ball boundary of bj close to each other, next to the c be the middle point, and then let's say all star is given by the radius L1 and L2, and tau is 1 over 4 times lambda and lambda 2, and lambda is given by the conductivity. And if K1 and K2 are larger than 1, then the gradient U at this x1 and x2 point is larger than infimum of gradient H dot normal derivative over 1 minus tau times constant times square root epsilon. So that term 1 minus tau becomes 0 as K1 and K2 becomes very large number. So the gradient U become very large, like 1 over square root epsilon. And for insulating case, we also have this lower bound. Now instead of gradient H dot n, we have gradient H dot tangential vector. And then about the upper bound, the gradient U is supernum is bounded by gradient H supernum divided by the same amount. So this theorem tells that the gradient U is bounded by 1 over square root epsilon if it is bounded by 1 over square root epsilon in the case K1 and K2 are infinite or K1 and K2 are 0. For example, if H is assigned in this direction, then the gradient dot n is not 0, so the blow-up occur. But if H is given like this direction, and since gradient H dot normal direction here is 0, so the blow-up doesn't happen. And in the case one of the inclusion is very small as the distance, then the blow-up doesn't occur. So we have similar result for the second case when omega is circular and then there's one inclusion. And now instead of giving entire harmonic function, we give Dirichlet constant or Neumann constant. And again, solution U is expressed in terms of double layer potential and single layer potential. And as we did before, the solution is given in terms of infinite series. So again, the location of reflected point is very important, and we get this result is very similar to the two inclusions case. Here again we have 1 minus sigma plus constant square root epsilon, so we have 1 over square root epsilon optimal bounds for this case too. Now let's give a closer look to the upper bound and lower bound. That when k is a large number, the gradient U is bounded by gradient H supernum over, here 1 minus tau becomes 1 over K1 plus 1 over K2. So this term becomes very small. So the term is like some constant times 1 over square root epsilon. So when epsilon goes to 0, gradient blows up. And if you look at the left-hand side, instead of supernum of gradient H, we have gradient H dot normal vector n. Now let's put H as tangential vector at the closest point between the two inclusions, dot with x. In that case, the left-hand side becomes 0 because we have tangential derivative, tangent vector dot normal vector. But the right-hand side still gives the blow-up. So in this case, from this case, we can guess there should be something more in this equation. I mean, this equation doesn't give clear idea when the blow-up happens. Again, the main idea is where the reflected points are located, and since we calculate normal derivative of iterated reflection H, so here we should take in a product with normal derivative with gradient H. So the one part is where the reflected points are located, and the second part is how this normal derivative times gradient H behave. And after doing some calculation, we can derive that after several steps, actually the reflected point, we can get some relation, get some result about where the reflected points are located, and based on that, the summation of the G1 is Jacobian of reflection function, and G1 at some reflected point times G2 at reflected point is bounded by some constant over x minus xc. X to the c is the center point between the bulb B1 and B2 plus square root epsilon. So what we can derive is if conductivities are large number, and assume that either gradient H is bounded by x minus x to the c. In that case, since the summation part gives bound 1 over x minus x to the c plus square root epsilon, that if we multiply this and this, then we can derive that the blow-up doesn't happen. And also if h is x2, so the gradient h dot normal vector is very small, in that case also the blow-up will not happen. So what you get here is we can decompose solution as two parts. The first one we say is use of S, and the second one is use of all. And use of all is bounded. So that use of all corresponds to the case when gradient H is bounded by x minus x to the c, or H is x2. So the remaining term is H is some constant times x1. If it's more than second order, then the gradient is smaller than O of x. If it is constant times x2, then the blow-up doesn't happen. So the only case when the blow-up happens is H is some constant times x1, if we assume the center point is the origin. So here, if we take out the center point, then Hn is like x1 function, so it is some constant that is given by gradient h dot n times x minus x to the c, so it's like hx is x1. And then all the remaining term we say is h minus hn, and the use of all is the solution corresponds to h minus hn, and us is solution corresponds to hn. And naturally we can guess that gradient ul is bounded even if it goes to 0, but gradient us will give good optimal bound. So here now you have gradient h dot n and gradient h dot n, so the left hand side and right hand side are given by their same form. The only difference is here in the lower bound term is given by 1 over lambda minimum, and then here upper bound term is given by 1 over maximum, but it doesn't change the blow-up rate. So now when we want to check the blow-up of gradient u, we only need to think about h is some constant times x1. And based on the theorem, we also can get estimate when the conductivity has non-zero complex part, so the permittivity is not zero, so it is some small positive number, and assume that h is given as harmonic function, and now h is complex valued function, and then based on the decomposition, we only need to care about h is constant times x1 term, and then again investigating the location of the reflected point, we get this result. So the US term is bounded by the small conductivity sigma 1 and sigma 2 plus permittivity part plus q root epsilon. So in the case the complex part is not zero, the blow rate is less severe. So instead of just sigma 1 plus sigma 2 plus q root distance, now we have one more term which comes from the positive permittivity. And again, the U all term is bounded. Now let me explain the given idea to get optimal bounds valid also for non-disk case. So he assumed that K is infinity, and then D1 and D2 are convex inclusions, and then he considered this equation. So Laplace U is 0, and then U is constant inside D1 and D2, and then normal derivative on D1 and D2 is 0, and H is again given entire harmonic function. And in this case, if C1 and C2 are not the same number, then gradient U is at least larger than the difference between C1 and C2 over epsilon. So if we estimate the difference between C1 and C2, then we get the lower bound. And his idea was use this H function. So H is again satisfied the Laplace H is 0, but instead giving the integral normal derivative ds is 0, he gave this condition. So integral on the boundary is 1 or -1. And then what we got is the constant on D1 and D2 difference is integral of d to h, capital H, ds plus integral on D2. Since h is given and then D1 is, this calculation still we need to some time, but yeah, here the main problem is to get h. If we get, explicit representation of h, then this integral, is just straightforward. So the question is, how can you get this h function? Now here is the case when we have two disks, then the h is very simple. Since when we have two disks, then we have using the Apollonius circle property, then we have one point where from the distance from the point to one circle is the same as distance from one circle to another circle. So using this property, h is the green solution of x minus some point divided by some number. But since log AB is log A plus log B, and then for the disk 2, again, the inside log we divide by the same number. So h is simply log at x minus p1 minus log x minus p2. The p1 and p2 are fixed point of the reflection. First take L2 and then L1. Second reflection we take L1 and L2. So we have two fixed points. and h is given by this fixed point. And in that case, integral on this is very simple. We only evaluate that the P1 and P2 point. And since P1 and P2 is like, constant given by the radius times square root epsilon, we get easily that the difference of the value on D1 and D2 is constant times square root epsilon. So if we divide by the distance between D1 and D2, that is epsilon, then the gradient is larger than some constant, depends on L1 and L2, times 1 over square root epsilon. So this, this is very simple idea to understand why we have 1 over square root epsilon blow up in L2. But if we want to do the same thing in the L3, the h is not simple like this. In L3, the green solution is 1 over x, then now 1 over x over some number, in L2, it's just simply separating, then everything is cancelled out. So h is simple like this, but in L3 it's very complicated. It's again infinite series. So after Gian having this result for all two convex inclusion case optimal bounds, he tried to derive the similar result in L3, and I also tried to extend the result in two-dimensional case to three-dimensional case, but we didn't succeed. And here is the result we got. So when k is infinity and assume that the potential difference is 0, then the gradient doesn't blow up. So it's very natural. This theorem means that the blow up happens because there are potential difference. And then naturally you can think that if the potentials are same, then there's no reason to have blow up. And then here comes the result by Professor Yang Lee and Bao and Lin. And they got result for L2 and L3 and the higher dimension as well, but I just focus on L3 case. And the equation is, again, Laplace is 0 and use constant on the boundary D1 and D2, and integral of normal derivative on ds is 0, and Dirichlet condition is assigned. And what they got is gradient u is bounded by constant times 1 over epsilon times log n. So that means C1 minus C2 is like 1 over log epsilon. And the important idea is decompose u as V0 plus constant times V1 plus constant times V2. Here V0 doesn't have potential difference, but V1 is 1 on boundary D1 and 0 on boundary D2. So it has potential difference 1. And V2 is 0 on D1 and 1 in D2. Again, it has the potential difference. So the here important term is C1 minus C2. And in their work, here is the lemma. The gradient u L infinity norm is bounded by the difference of the constant over epsilon plus phi C2 norm on the boundary. And here the C1 and C2 is given by this number, and this phi epsilon phi, there should be some log epsilon term. Okay, so as we get the condition in L2, so when h is x1 direction, then there is blow up, but in x2 direction there is no blow up. So if you look at the left hand side, is this q epsilon phi is small, then the blow-up doesn't happen. But if it is large, then the blow-up happens, and the blow-up rate is 1 over epsilon times log epsilon. And it was 2007, after we know that here there's a result, good result like that, and then Mikyoung and I, we met in the conference in Beijing Normal University, and then Mikyoung explained me a new proof using his calculation in L2, and then we want to use that new calculation to get some result. So and the result is to get optimal bounds in terms of the radius as well. So here, the question is how the geometric conformation, the radius, influence the blow-up rate. So in the estimate here, this constant is some constant depends on the boundary of D1 and D2. But Mikyoung and I, we restrict the domains to be just spheres, and then get some estimate for C, to represent it in terms of L1 and L2 as well. So the main idea was, again, that Mikyoung's method to calculate an L2 general shape domain. So here H is satisfy this equation, plus H is 0, and then H is constant on D1 and D2, and then normal derivative is 1 or negative 1. So U minus U on D1 minus U D2 is given by this integral. And if we get this difference, then the U, gradient U is bounded by U on D1 minus U on D2 minus epsilon. And the question is, how can we get this H? This is the problem part. So in L2, it is just log of x minus P1 minus x log x minus P2. But in L3 case, it's infinite series. At first, we get 1 over x at the center point, and then to make it neutralize, we should add one more term, which to make H to be constant on boundary D1 and D2. So gradually we just match to add one more term, and then get this infinite series, and this H satisfy this equation Laplace. H is 0, and then normal derivative integral is 1 or negative 1. And all these quantities are related with, again, reflected points of the centers of B1 and B2. So, all of these estimates, it's very related with the reflection. And we carefully calculated where the center point move, and then here is the result. When H is this linear function, then the U on D1 minus U D2 is 1 over log epsilon times L1, L2 over L1 plus L2. So now we understand how this radius influence the blow rate. It is just, multiply the radius and divide by L1 and L2. So let's review what I explained. First, I explained what is the problem that is create an estimate. So in the L2, there are 2 circular inclusions or 1 circular domain omega and inclusion B, and then the conductivity is assumed to be constant, and then we derive the optimal bound when k is positive number. So based on this estimation, we understand how the conductivity and radius of the discus and then the distance is related with the gradient U supernorm. And then we decompose U to be U sub S plus U sub R, which is one blow-up term and then one non-blow-up terms. And we know that U blow-up only when H is some constant times X1. We assume that B1 and B2 are in the X direction. And then all other terms like X in higher dimension term or X2 direction term, there is no blow-up, so we only need to care about the X1 direction term. And based on that, we derive also for the case of positive permittivity case. So when conductivity are very small, then the blow-up rate is 1 over conductivity plus permittivity plus square root of the distance. And then this spherical inclusion case, we strongly rely on the idea of Mikyoung's result. So derive auxiliary function H, and then based on that, the constant difference is integral with the H on boundary with given harmonic function H, and then based on that, you get the blow-up rate in terms of R1 and R2 and epsilon. Thank you.
Any comments or questions?